Okay, so start with mechanics, which we'll be doing for probably pretty much up to Easter, I think. I want to start with forces and friction and resolving forces. The idea here is that if you've got two, this is my shorthand for perpendicular if you're not used to it. If you've got two perpendicular components of a force, they're independent of each other, so they don't affect each other, which I think we've looked at before. So it's quite useful to resolve forces into two perpendicular directions. Normally you resolve them so that one component is in the direction of motion and the other component is perpendicular to it, but we'll talk about that as we go along. So resolving forces, essentially what I'm doing, so here's my force 9 newtons, positive x, positive y axis. So we're just going to start by writing these as vectors essentially. So we've got a bit going along here and a bit going up here. So there are two perpendicular directions. So I essentially want the adjacent to find how much of this force is acting in the positive x direction. And we know that cos of 40 is equal to the adjacent over the hypotenuse. So we've got the force sitting on the hypotenuse, and so the adjacent is equal to 9 cos 40, and that's the component of this force acting in the positive x direction. And once you get used to these, you'll literally just be able to write them straight down. So 9 cos 40, that gives you to 3 sig fig. So we're on 3 sig fig at the moment. As soon as we start using G, we'll be going to 2 sig fig. And then the amount on acting in the positive y direction, similarly, is equal to 9 sine 40, because we want the opposite, and the opposite divided by the hypotenuse gives you sine 40, and then you just pop that into your calculator. And so you can now write that as a vector, and that gives you 6.89i plus 5.79j. Or you could write that in column notation if you wanted to. I'll just do a couple more so you get a feel for it. So they're both acting in a positive direction. If we look at this one, so I've got a force of 20 newtons acting 65 degrees, like so. Then the same deal, basically. So in the x direction, because this is the positive x direction, this is acting in a negative direction. So I'm going to put that negative on there, and then it's 20 cos 65 to get to the adjacent. So negative 8.45 newtons. And then to get to the opposite, which will give me my y, and that's acting in the positive y direction, so I don't have to worry about changing the sign. You get 20 sine of 65, which is 18.1. And so as a vector, that's pretty straightforward from there. You get that, and I'll just do one more. I might need to put that line up a bit higher, sorry. So we now have an angle of 18 degrees. and a force of 100 newtons. You could do 90 minus 18, which is 72, and work with it from there, and then it will be similar to the other two in that you've got the angle between the force and the x-axis. Or if you work with 18, just to show you the difference, then the x now is opposite the angle, and we're going in the negative x direction. So I'm just trying to find this bit across here. So that's going to be minus 100 sine 18, because I want the opposite. And in the negative y direction, I've got minus 100 cos 18, and that gives you negative 30.9 newtons and negative 95.1 newtons. And again, you could write that as a vector. Like so. Alternatively, you could do this question. So you could instead work with that as being 72. And then in the x direction, you've got 100 cos 72. And sine of 90 minus theta is the same as cos of theta. So it all matches up. I'm not particularly wanting you to rewrite them, but just to sort of show you that, yeah, it is the same thing, so to speak. So if you want the adjacent, it's the force cos of the angle, and if you want the opposite, it's the force times sine of the angle, with your force sitting on the hypotenuse. So if you just start by doing some of those just to get a feel for it, and then we'll move into some specific examples.